This lecture is about plate bending theory. Bending of plates and beams is a case of a degenerations of the 3D continuum mechanics. So here I have a three-dimensional element. The dimension of this cross section is A and the length is L. If A is much lower than L, we can convert this three-dimensional element into one-dimensional element. A center line with a cross sections. This beam is going to have 3 translational degrees of freedom. 1 translational degrees of freedom along the element, another 2 that correspond to deflections. It's going to have 3 rotations. 2 rotations correspond to the deflections, and another additional rotation that correspond to the torsion, that is a rotations of the cross sections along the axis of the center line of the beam. The other case is when L is much lower than A. So we can convert this three-dimensional element into a two-dimensional element. That is called the shell. The shell is going to have 3 translations, 2 translations along the plane, and deflections perpendicular to the plane. And these deflections will produce 2 rotations in each point. Let's make a summary of the finite elements that we introduced in 1D and 2D. So this is a frame of one-dimensional elements. So we can classify these elements into bars. In 1D, a bar has only 1 degree of freedom. The beam in 2D is going to have 2 degrees of freedom. There is going to be 1 deflections and 1 bending rotations. But in 3D, it's going to have more degrees of freedom. It's going to have 2 deflections and 2 bending rotations. The other element is the flexural and torsional member. So you obtain this one by combining the bar with the beam and introducing the torsion. So it's a fully three-dimensional, it's one-dimensional elements with three-dimensional degrees of freedom, 3 rotations and 3 translations. And finally, we have the cable that is a one-dimensional element where there is no significant bending moments. In 2D, we can introduce corresponding elements to these ones in 1D. So we have the plane stress and plane strain axisymmetric element, plane elasticity analysis, that is the corresponding to the bar element in 1D. But we can generalize the beam theory to get the plate theory. That is like the bending theory in 2D. And the shell correspond to the integrations of the degrees of freedom of the plane elasticity element with the plate element. And the counterpart of the shell is going to be the fully fractional torsional members in 2D, in 1D. Finally, we have the membrane, that is the counterpart of the cable in 1D. So all these elements we can construct as one-dimensional members or two-dimensional members. Okay, let's go to the plate theory. So this elephant represents a non-uniform distributed load that is going to produce a deflections in a two-dimensional surface. So the plate bending theory, similar to the beam theory, is a degeneration of the 3D classical continuum theory. So we are assuming that lines normal to the mid-surface before deformations remain straight and normal of the mean surface after deformations. So this is a cut of the surface, so it's going to have a certain thickness T. This is the mean surface. Any surface above or below this mean surface, distance z from the mean surface, is going to have a certain plane stress represented here by sigma x and sigma y. So let's put a straight line. This is a straight line in the mean surface. We are going to assume that this line remains straight after deformations. Straight, but it can rotate along the x directions or can rotate with respect to the y directions. So this is the assumptions. And the deformation is given by deflections in this direction z. This deflection is called W. So these assumptions allow us to reduce the problem from a 3D problem to 2-dimensional problems. But the rotation of this line will introduce additional degrees of freedom. These are the bending rotations, how this line in every point of the surface is going to rotate. Let's review the plane stress elements. We need these plane stress elements to construct our shell element. In this element, every point has 2 degrees of freedom that are represented by 2 displacements, u and v. So it's a plane displacement. So the actions in this plane stress are plane forces. So the forces only act on the plane. And the balance equations is written like this, where this is the differential operator. The kinematic equations is the relation between the displacement vector, that is the uv vector, and the strain, taking the derivatives using this L operator. And the constitutive equations is the relations between the stress and the strain. In our case, is this D matrix, where E is the Young modulus, nu is the Poisson ratio. These are the governing equations of the plane stress element. Now we are going to introduce another 2-dimensional element, that is the plate element. In this element we have W, that is the deflections perpendicular to the plane, and this deflection is going to produce 2 bending rotations, one in the x directions, another one in the y directions. So the degrees of freedoms are going to be 1 deflections and 2 bending rotations. The external actions is a load per unit of area, that is the weight of the elephant. The balance equations, yes, write this from here, is a generalizations of the bending theory. I'm going to have here 3 moments, bending moments, and they are related with Q, that is the action that is load per unit of area. The L operator is given by this differential operator. The kinematic equations will define the curvature of these deformations. So the curvature are going to be a set of second derivatives of the deflections that can be written like this in terms of the same differential operator. And the constitutive equations is similar to the one in the beam, but it is going to be 3 by 3 because we need to relate 3 curvatures with 3 moments. So here you are going to have a matrix in terms of the Young modulus, the Poisson ratio, and the thickness of this plate. So these are the governing equations of the plate element. Now we are going to mix these two-dimensional elements. So we have the plane stress element that has 2 degrees of freedom in each point, and we are going to combine it with the plate element that have 3 degrees of freedom in each point, is the deflections and 2 bending rotations. If you combine these two, you get the shell element. This shell element in every point is going to have 5 degrees of freedom, 3 translational degrees of freedoms, and 2 rotational degrees of freedoms. So you can see here that these rotations along the deflections that in the beam correspond to torsions doesn't appear here. This degree of freedom is often called drilling degree of freedom, but it's spurious degrees of freedoms with no meaning here. So it's 5 degrees of freedom. So in summary, we have the shell element. So it has 5 degrees of freedom. So 1 deflections, 2 plane displacements, and 2 bending rotations, and 1 spurious degrees of freedom. The external actions is going to be plane force, forces on the plane, like coming from the plane stress element, and load per unit of area that comes from the plate element. So you can have a flat plate that can be generated in strand 7 using quad 4 elements, but you can have a curved double curvature plate that is in the literature is called more shell, but in strand 7 everything is called plates. So every point have a curvature that is not a number, but it have 3 components, and these curvatures produce moments. The curvatures and the moments are described by the theory of bending of plates. Here I want to introduce some interesting example of shell structures. So this is a shell with 1 curvature, and this is spherical sections is a shell with 2 curvatures. And the 2 curvatures are the same, but it's curved in 2 different directions. This is curved only in 1 direction. So which one do you guess is stronger? So the material is the same. Which is going to be stronger? So I guess this one is going to be much stronger. This is a strength that doesn't come from the materials itself. It comes from the geometry, from the curvature. I have also this interesting bridge that is called the Trumpf footbridge in Germany. So this bridge is made with shell. It's steel, galvanized steel. The interesting things in this bridge is that it's extremely thick. The relationship between the thickness of the shell and the length of the bridge is 20% less than the corresponding dimensions of an egg shell. And we have this kind of cantilever structures, but these the bending stiffness of these structures come from the geometry. So this looks more like a corrugated roof. We have a curvature, especially in these directions, but when this material bends, it produces a curvature in the other directions. So it's going to have a double curvature. And the curvature itself make the material much more rigid than if it doesn't have the curvature. And finally, we have these examples of roof with double curvatures. They are not very common today, but I guess they are going to be more common because there is a possibility to produce these structures that doesn't necessarily need to be steel reinforced by 3D printing. So the tensile stresses in this structure can be compensated with the geometry, with the curvature.